Hi, and welcome to this episode of Office Hours with Professor Eric Bogatin. I'm Eric Bogatin. In this episode, I'm going to review a few free animation tools that I find incredibly useful to help us understand and visualize the dynamic nature of signals on interconnects. This is one of the most important essential principles in signal integrity that I think is important to grow our engineering judgment with. For more details about these tools and where you can download them and use them on your own, I invite you to check out my Substack column. You can click on the QR code over here on the right, and that will take you to the Substack column, and you can access the links in the Substack column. And you can access the links in my Substack post for December 1st, 2025, and read the descriptions about these four tools that I'm going to introduce you to. So with that, let's get started with the first tool. The first example of the free signal integrity animation tool that I'm going to show you is about current propagation in a transmission line. It's really simple, but it gives you a really good feel for how signal and return currents propagate on a transmission line. Let's open it up. After you click on the links that are in the Substack post for December 1st, you'll be able to access executables for all four of these tools. And when you download them, be sure to open up the first one about current propagation. Here's what it opens up to, and it's a really simple example. This is kind of a perspective drawing of a transmission line. This happens to be microstrip. Doesn't really matter what the nature of the transmission line is. The principle is applied to all uniform transmission lines. There's a signal conductor and there's a return conductor. Now, sometimes you think about a rough approximation for a transmission line in terms of little L's and C's. It's not a very good approximation, but it's a starting place. You really want to change your engineering intuition about the behavior of signals propagating on transmission lines to not think in terms of L's and C's, but think in terms of propagating fields. It's that electric field that propagates. When we launch a signal between the signal and the return conductor, we change the voltage between the signal and the return. That changing voltage is a changing electric field. That changing electric field creates a changing magnetic field. The changing magnetic field creates a changing electric field, and it self-propagates. We think about that signal as that voltage between the signal and the return conductor propagating down the transmission line. Equally important, though, is the current. And that current is going to be propagating between the signal and the return conductor and returning through the dielectric material where there's changing electric field. And a changing electric field is a displacement current. And so we're going to have conduction current propagating down the signal line, returning to the return conductor through displacement current, back to conduction current, back through the return path. And that signal is going to propagate, the voltage is going to propagate, and the current waveform is going to propagate. That's what we're going to illustrate. So we're going to turn it on. And when we turn it on, and I'm going to come over here to the controls, and I'm going to just step it forward to stop it here for this instant so we can see that signal propagating down the line. This is effectively a plot of the voltage between the signal and the return conductor across the line, highlighting this beginning region here where the signal is. Over here, the signal hasn't gotten here yet. The voltage is 0 between the signal and the return. Over here, the signal has passed by, and we have a constant voltage between the signal and the return conductor. Yes, we have electric field here, but it's not changing. There's no return current in this region. The only place we have return current flowing in the displacement current between the signal and the return is where the electric field is changing, and that's where the voltage is changing. So it's right here at the wavefront. And as this edge moves down the transmission line, we're going to see that signal propagating down, the return current returning right where that edge is. I'm going to turn it on again. We're going to watch that signal return propagate down the line. And so here's that signal return, signal return, signal return. In addition to the voltage wavefront, there's also a current wavefront propagating down the line until it hits the end. So we want to adjust our engineering judgment to be thinking about this signal propagating, signal return, signal return, signal return, where that changing voltage is. There's a voltage wavefront, electric field wavefront. There's also a current wavefront propagating down the line. And that current has two directions. It has a direction of propagation as it goes from left to right, down the line, and it has a direction of circulation. In this case, circulating in this orientation in the clockwise direction. If it's an increasing voltage, 0 to 1 volt, it's increasing the return current is circulating in the clockwise direction. If it was a decreasing voltage that was propagating in this direction, it would be return current. It would be return signal, return signal, return signal. This is a useful illustration to get clear in your head how signals are going to propagate down the transmission line and how the voltage wavefront propagates and the current wavefront propagates. The next animation tool is going to describe what happens as that current and voltage wavefront encounters changes in the instantaneous impedance. The second animation tool we're going to look at is an animated TDR. After you've downloaded the executables from the links in the post on my Substack site, you're going to want to open up the TDR viewer as part of the Signal Integrity Academy. And here is that TDR viewer. This is a little more complicated an animation tool, but it gives us a lot of flexibility. Now I want to point out that this isn't really a simulation tool. Yeah, there's some numbers that are being calculated, but it's only coarse values. You don't want to use this tool in lieu of a SPICE simulator. We want to use this as an animation tool to help us keep track of the propagation of the signals back and forth on the transmission line. The first step we're going to do is set up the geometry. And if you come over here to the right hand side, we have a couple different sections of transmission lines we can construct automatically. We have 3 different series transmission line segments, and then we can add a stub. So I'll just show you the 3 parts here. Here's section 1, 2, and 3. This is the top view. The yellow is kind of like the signal line. The green is the return path. And in here we're going to plot the voltage that dynamically propagates between the signal and the return. So one configuration is uniform, at least 3, at most 3 sections of uniform transmission lines. The fourth type of structure we can create is a uniform transmission line with a stub in it. And this is useful thinking about reflections from stubs. For now, we're going to take a look at the 1-part transmission line. Of course, a transmission line is defined by a characteristic impedance and time delay. So for this section, we can find a characteristic impedance. We'll keep it 50 ohms. We'll keep the time delay. We'll make it a little larger so we can make it a little bigger on the screen. We make a change, we push enter, and the geometry is reflected in the change that we've made. The next thing we can do is change the source impedance. And so we do that over here at the signal generator. We have a couple different waveforms that we can use. I personally like the step edge, but you can experiment with other kind of waveforms over here. So in addition to the step edge, we can change the rise time of that signal and the source impedance. Those are basically that and the voltage are the 3 most important terms that characterize the source. So we'll keep the 150 picoseconds, but we'll make the source impedance really small. In this case, we'll make it 5 ohms. And then lastly, at the far end, we can change the load impedance. And I'm going to make that 1,000 ohms. Now there's a limit to how high an impedance we can go, but 1,000 is plenty high for our applications. So I've made these changes. I have to push the enter button, and now we're ready to calculate. What we're going to do is we're going to generate a voltage from this source. It's going to come through this source impedance, and now it's going to enter the transmission line. And so we've created a voltage divider. And if you're a little confused about this, you want to check some of my lectures in the masterclass on principles of high-speed digital design or transmission lines, where I talk about how to think about the input impedance of a transmission line. So we go from that 5 ohms to the 50 ohms, 1 volt at the source. Most of the voltage appears across the 50 ohms, but we get 50 divided by 55 ohms is the sum, so it's 50 over 55 ohms times 1 volt. That's the voltage launched in the transmission line, close to 1 volt. It's going to propagate along as these 50, 50, 50, and then it's going to hit the high impedance, and what it's going to do, reflection coefficient is basically 1, it's going to reflect and head back. So now we're ready to do that calculation, and we're going to watch that signal propagate. The best way to use these tools, it's not really to learn first from scratch about signal integrity. It's really to confirm your engineering judgment and kind of verify your understanding. And that's where I think it's really important to apply rule number 9. Think about what you anticipate you should see, and then the tool will help confirm that for you. So before we start, we're going to see that signal launch down the line. It's going to propagate uniformly. When it hits the end, it's going to reflect, and the reflection is going to be 1, and so whatever goes in, we're going to see it coming out. And we want to look at the voltage that we would see at the end here from the two waves, plus that instantaneous voltage. So let's run it, and I'm going to stop it partway through here. So here's that signal launched down that line. Here's that not quite 1 volt edge. It's 50 over 55, so it's like about 91% of 1 volt propagating this way. It's going to keep propagating, seeing that instantaneous impedance. It's going to propagate until it hits the end where it sees the reflection coefficient, and so here it's reflected. So we had a 1 volt going in, we have a 1 volt coming out, and so what do we have at the receiver here where we have the 1000 ohms? If we stick our scope probe, we're going to measure 1 volt going in, 1 volt reflecting back, two signals propagating in opposite directions. They're going to add, we're going to get 2 volts over here at the receiver. And that signal, that 1 volt signal that was heading to the right, it reflects, it's going to head back to the source, and as it propagates, the net voltage that we're going to see along the line is going to increase because both voltages are positive voltages. They're both positive changing voltages. And so we're going to see this positive voltage propagating down the line until it gets to the transmitter. And what's at the transmitter is this 5 ohms, and so it's going to reflect. It's going to be a negative voltage reflecting, and we're going to see a drop. So let's watch that. Here's that positive 1 volt propagating. It's going to hit that negative voltage, and there it is. And look, here's that voltage that was going in, the 1 volt. It changes sign and then reflects. And so the voltage that we see here is that initial voltage minus the reflected voltage because it's got the opposite sign. And now it's going to continue propagating down the line. And we're going to watch that negative going voltage propagate down the line. And here it goes, hits the end, reflects, and it's a negative voltage that reflects, heads back, changes sign, it's a positive voltage, and now you get the idea. We're going to see this ringing that's going back and forth between the transmission lines. And this shows the dynamic nature of that signal as it's propagating back and forth, hitting all the high impedance at one end, the low impedance at the other end. And you can see that characteristic nature of the ringing that we see over here at the receiver end. This tool allows you to explore the dynamic nature of the signals propagating back and forth as they encounter discontinuities. Let's do one other example here. I'm going to use a 3-parter. The first one will be 50 ohms. The second one will be let's make that a high impedance, 100 ohms, and we'll make it really short. The first one will make 2 nanoseconds. The second one we're going to make, let's see, our rise time is 150 picoseconds, so we're going to make it 0.15 nanoseconds as well. And we'll make it 50 ohms, and we'll make the load 50 ohms as well so that we don't have any reflections there. And we push enter, locks it in. There's our discontinuity, and now we're going to watch the reflection from that discontinuity head back and bounce off of that low impedance. So let's watch that signal, and here we go. So here's that signal, hits the end, we see the bouncing back and forth, hits the end, reflects, bounces back and forth, and we see a combination of the reflections from the discontinuity back to the source, that's basically the TDR, and we see the impact in the forward direction as well. And this is where a discontinuity can have an impact on the received signal. But you can see that it doesn't happen at the leading edge necessarily, it happens a round trip time between those discontinuities later. So using this tool, it allows you to visualize the dynamic nature of those signals reflecting back and forth, encountering impedance discontinuities, and reflecting and transmitting. It's really designed to help reinforce your understanding. And so before you run the simulation, always think about what you expect to see. And now you can play with it and try different geometries, different structures, and then you can test your understanding of what you expect to see at the receiver and at the transmitter. The third tool I'm going to illustrate that you can download in the collection of the four free animation tools is about crosstalk. And so when you open up the link that has the 4 different files, double click on the executable that says crosstalk simulation. And here's what we get. I'm going to make it bigger so we can see all the details. This is probably one of the most useful tools that I've come across in order to illustrate what really happens with crosstalk between transmission lines and why the dynamic nature of the signals is so important. What we're illustrating are two transmission lines. There's one up here, here's the signal line, the return is underneath it, and here's the second one, here's the signal line, and the return is underneath it. We're going to define a coupled region, and that coupled region we can make bigger or smaller by moving the little caret down at the bottom. And we can select two types of transmission lines, either a strip line or a microstrip. And so for now, I'm going to use the microstrip. This is the cross section to show here's the signal, here's the return. And what we're going to illustrate is the behavior of how near end and far end crosstalk is generated and why we see a different signature for near end crosstalk versus far end crosstalk. So we're going to send a signal down the transmission line. This is going to be the aggressor. We're going to look at the victim transmission line over here, and we're going to plot the voltage on the signal and return conductor dynamically and on the aggressor line as well. For now, I'm going to start with one coupled region. And so we're going to send an edge through, and we're going to look at the capacitively coupled current and how it propagates backward and forward, and the inductively coupled current and how it propagates backward and forward for the case of microstrip. We can look at the capacitively coupled current only, the inductively coupled current only, or the total current at the same time. Let's do the capacitively coupled initially. And again, you want to apply rule number 9 when you do this analysis to think about what you expect to see. So let's see, we send a signal down here. Here's the edge is going to propagate this way. We only get crosstalk where we have the dVdt or the dIdt between the lines. That's where we have the edge. That's where we have the dVdt that induces voltage noise on the quiet line, and that's where we have the dIdt that inductively couples a current loop on the quiet line. And when that voltage noise gets to the quiet line through capacitive coupling, it's going to split. We're going to equal amounts going in both directions. And when the inductively coupled current hits the aggressor, hits the quiet line, it's going to split as well, but it has not only a direction of propagation, but a direction of circulation. And if the signal return current is going one way in the aggressor, it's going to be induced in the opposite way in the victim. And that means it'll look positive going back and it'll look negative going forward. And let's first watch capacitively coupled current. So here's this edge propagating, and I'm going to stop it right here before it gets to the coupled region. When it gets to the coupled region, we're going to get that capacitively coupled current. We're going to get that capacitively coupled voltage induced in the quiet line, and we're going to see it split and move in both directions. And here it goes. So here it is in the victim line. Here's that capacitively coupled current heading back that way and in the forward direction. And it makes its way to the far end. And you can see the signature of the waveform looks basically the same at the near end and the far end for that single pulse. But now let's add a couple. Let's make the coupled region a little bit longer, so we have a few more of these pulses that are going to be generated in the quiet line. Now let's watch that capacitively coupled current. And so we get it generated here. Let's see, we get a little bit over here, a little bit over here, a little bit over here, a little bit over here. These are all adding up. They're all generated where that edge meets the coupled region at different times, and they have to dribble back. They have to get to that region and they have to come back. And so there's a time delay between them based on how far down the line that coupled region is. But the far end noise, the noise that's propagating in the forward direction, the coupled noise is propagating at the same rate as the signal, and they're just adding up and they're getting bigger and bigger. And now we begin to see the different signature at the near end and the far end for capacity coupled current. Now let's look at inductively coupled current. And so we'll look at one coupled region. So here's this edge propagating along. It's going to encounter the coupled region. It's only where I have the dVdt, in this case the dIdt, that we have inductively coupled current. And there it is. And you can see the positive, so the signal return current in the aggressor is going in the clockwise direction. It's going to be induced in the counterclockwise direction. And that propagating from right to left in the backward direction, clockwise or counterclockwise current is going to be a positive voltage. And we see that positive voltage moving down the line. But in the forward direction, it's still circulating in the counterclockwise direction and propagating from left to right. It's going to be a signal, it's going to be a return signal, return signal, return signal, and we're going to see it as a negative voltage. And so when it hits the end, we immediately see this difference in the signature in the near and the far end crosstalk from inductively coupled current. We see that it's positive at near end, just like capacitively coupled current, but it's negative in the far end with the inductively coupled current. And if we go ahead and we make our coupled region longer, and we look at the inductively coupled current, we see the inductively coupled current in the same way. It's going to be generated at one location and then split and head back and head back and head back and head back. And we see it dribbling back, and it's going to be building up in the forward direction. It's generated different locations moving forward at the same rate the signal is, and it's just building up with snowballing. And we see the large negative voltage at the far end. And when we combine them all together in microstrip, the inductively coupled current is larger than the capacitively coupled current, and so we have a net negative voltage in the forward direction. So let's take a look at that when we do all of them. So here we have the total current that is going to be propagating in the backward direction and the forward direction, and we see that we get both the capacitive and inductively coupled current is positive, moving in the backward direction, but they're in opposite direction, moving in the forward direction, opposite polarity, moving in the forward direction. The net result of this, though, is there's more inductively coupled current, and we see a net negative voltage. And that's why we have a very different signature for near end than far end crosstalk. This, I think, illustrates that really well. If we use strip line, what we're going to find is that the capacitive and inductively coupled currents are the same magnitude, and so even though that they are generated in the victim line, they're going to propagate in the forward direction, they're going to cancel out, and they're going to add in the backward direction at the near end, they're going to cancel out in the forward direction, and so we're not going to see any of that far end crosstalk for strip line structures. And we see no far end crosstalk, and if I increase the coupled region, we'll speed it up a little bit now that we know what to expect, and we'll look at the total amount of coupled current. It's propagating in the forward direction, it cancels out in the forward direction, no far end crosstalk in stripline. So I find this tool incredibly useful in order to think about the dynamic nature of the signals. It's the dynamic nature of the signal propagating and the nature of the induced currents and voltages in the quiet line that gives rise to the very different signature for noise at the near end versus the far end. The last animation tool I'm going to illustrate for you is about how return loss gets its ripples. This is a very subtle feature and yet really important and really common in the return loss when we look at the S parameters of virtually every interconnect. So the last animation tool, let's open up, and I'm going to walk you through it very briefly so that you can then play with it and get a good feel for this idea of the creation of the ripples. So here is the tool, and it's really simple. Here's the setup. We've got 50 ohm ports, and we've got a uniform transmission line whose impedance is less than 50 ohms. We're going to send a sine wave in. Here it is in red, and it's going to go down the transmission line. And first, initially, we're going to sit over here where the electrical length is really, really short. And that means that there's the same voltage everywhere down the line. It's really, really short electrically. There's no phase change. And we see that over here as every place on the line having the same phase. So the signal goes in. There's no phase change as it enters the transmission line, but we do have a reflection from the front interface. And because we go from 50 ohms to a low impedance, the phase change is negative. So here's the signal going in. Here's the signal coming out. And so when you look at that signal that's going in, here it is, it's decreasing and it's about to increase, and here it is decreasing. The reflected wave has a 180 degrees phase shift from the incident wave, and that's propagating this way back to the source. So let's follow this wave as it goes down the line, hits the end. We go from low impedance to high impedance. There's no phase change because it's the second impedance, that's 50 ohms, divided 50 ohms minus, call it 30 ohms, over their sum. It's a positive amount. And so when this wave hits the back end and then reflects and heads back, there's no phase change. Whatever the phase is going in, that's the phase of the wave propagating this way. And because it's electrically short, the phase of the wave coming out here is exactly the same as the phase of the wave going in here. But because of the 180 phase change and going from 50 ohms to the low impedance over here, because this is reflected, gave us a 180 phase change. There was no phase change in propagating down, reflecting, coming back. These two, you can see, are 180 out of phase, and when they are collected by the receiver over here, they're going to interfere and they're going to subtract. And so we're going to have a minimum in the reflected wave because of the 180 phase change on the first interface and no phase change on the second interface. And so if our interconnect is electrically short, there's not going to be any reflection from it. It's going to look electrically transparent. It's one of the definitions of electrically transparent is electrically short, almost independent of what its impedance is. And so that says at the lowest frequency, we ought to see a reflected signal that's a large negative dB value. And the transmitted signal, well, let's see, most of it goes through, and I see it coming through. We get this reflection over here. There's another reflection from the 30 ohms to 50 ohms. It goes from low to high. There's no change in phase, and so the reflection off this front interface when it comes through and comes out is the same phase as the first pass signal. These are in phase. They're going to add. We're going to get a maximum in the transmitted signal, and that's why S21 is a maximum close to 0 dB at the lowest frequency, and the return loss is a large negative dB at the lowest frequency. And then we're going to increase the length of the line. And here we're going to make it exactly a quarter of an inch. And so when it's a quarter of an inch, we have, let's start that propagation going here. We have the wave going in. There's going to be a quarter wave change coming out here. It's going to propagate another quarter wave, and so these two waves, the first reflection and the second reflection off the back, they are in phase. So you can see them here. They're going to add. That means we're going to have a peak at a quarter of a wavelength. When the length of this interconnect is a quarter of the wavelength of that frequency, we're going to have a maximum. We're going to have a maximum in the reflected signal S11, and we're going to have a minimum in the transmitted signal S21. And if we make it a half a wave, then we reach the point where this guy has gone a half a wave hitting here, another half a wave, and so the reflection here is 180 degrees out of phase. This wave now is a whole cycle change. These are still 180 degrees out of phase. They're going to interfere. We're going to have a minimum in the S11 when the length of the interconnect is a half a wavelength, and we're going to have a maximum in S21. And so as we continue making the transmission line longer and we go through these multiple quarter wave steps, we're going to see successively min and max in the return and the insertion loss. And this illustrates what those waves are doing and why we get the ripples in the return loss because of the interference between the reflections from the first interface and the second interface of that transmission line. I find this, again, a very useful tool. You're not going to necessarily learn from scratch how the waves reflect, but if you apply rule number 9 and you come in having an understanding of where the of how S11 is related to the reflections from the first interface and the second interface and the multiple reflections, if you have an understanding of that, this illustrates those very clearly and helps to cement that understanding. And that's really the purpose of all 4 of these tools. It's not to learn from scratch, but it is to reinforce your understanding so that you have that engineering judgment or engineering intuition about how signals propagate on transmission lines and how their dynamic nature influences the behavior of how they interact with interconnects. So I hope you enjoy playing with and exploring these tools. Be sure to share them with your colleagues, and you can and going through the process of explaining how these tools illustrate the dynamic nature of signals will help reinforce for you how to think about signals propagating on interconnects and increase your engineering judgment.